All right, so the simple definition is we're going to be studying heat, and we're going to be looking at its relationship to the mechanical energy of the molecules. We have to unpack this statement. Number one, what's heat, what's mechanical energy, and what are molecules, right? So mechanical energy is something that we understand at this point. It's a combination of kinetic and potential energies, and it's a combination of kinetic and potential energies of the molecules. We're talking about molecules. We're talking about their kinetic energies and their potential energies. We know what kinetic energy is. Kinetic energy is the energy of motion. So if these molecules are moving, they got kinetic energy, right? We also know something about potential energy. Potential energy is the stored energy. We know something about the stored energy. As far as we were concerned, the stored energy is going to depend on the height of the object that you're looking at. So height of the molecules is not the best interpretation for potential energy. So potential energy is going to be somehow related to the relative position of these molecules. The relative position of these molecules with respect to each other. That's what the potential energy is going to be. So the question is heat. What is heat? And how is heat related to the mechanical energy of these molecules? Well, something about heat that you know, it's a form of energy, right? And it flows somehow. And you know that's going to flow from hot to cold. So heat is a form of energy that flows from hot to cold. That's as far as you know. And then something happens when it's flowing. Something is going to happen to the molecules. Somehow it's going to affect the motion of the molecules and relative positioning of these molecules. All right, so that's what we will study in thermodynamics. So it's the study of heat and its relationship to the mechanical energy of the molecules, in essence. Let's start off with a few observations.
For example, people tell you to put flowers in the refrigerator. Well, the extreme cold of liquid air really isn't very good for flowers. Let me show you. Interestingly enough, it doesn't change the way the flowers look very much. When I pull them out, they look pretty much the same, but it has made them just a little bit brittle.
So here's a question for you. What made the flowers brittle? You have an idea, right? In the back of your head, you're thinking, oh, the flowers just froze. They're made up of cellular structures, 80% water. So the water freezes, so the flowers are frozen. Hence the reason why they became brittle. That's the way you will think of it. All right, but there's more to the story than that we will dive into. All right, so let's start off with temperature. So, you know, heat is a form of energy that flows from hot to cold. And how do you know what hot is? How do you know what cold is? Obviously, you can feel it, but you can also measure it. So the temperature is the measure of how hot or cold something is. Let's go with a simple definition first. And then we will expand on it. So you get to measure the temperature. So the question is, how do you measure temperature? Well, you measure temperature.
No one needs to suffer with
using a thermometer, right? So speaking of using a thermometer, with this particular one that you're looking at, is measuring temperature in terms of Fahrenheit, because that's what we do in the United States. Outside of the United States, we use Celsius. In sciences, including physics, we use Kelvin temperature scale. So there are 3 different temperature scales at work. All right, so regardless of which scale you're using, there's a purpose to measuring temperature. You measure temperature to see if there's any temperature difference between 2 regions. All right, so you measure the temperature at this region, you measure the temperature at a different region, and if they're at the same temperature, there's no heat flow. This system is said to be in thermal equilibrium, which means that there's absolutely no heat flow. All right, so you measure the room temperature, you measure my coffee temperature. If they're at the same temperature, they are in thermal equilibrium. There's not going to be any heat flow. All right, so heat is going to flow when there's a temperature difference. It's always going to flow from hot to cold. If coffee is hot, the room is not, then the coffee is going to cool down. It's going to cool down until it reaches the room temperature. That's what it is. So this is known as the zeroth law of thermodynamics, according to which if there's no temperature difference, there's no heat flow. All right, so the purpose of measuring temperature is check to see if there's any temperature difference. If there's any temperature difference, there's going to be heat flow. Heat is going to flow from hot to cold. If there's no temperature difference, there's not going to be any heat flow. All right, so the zeroth law talks about, hey, no temperature difference, then there's no heat flow. That's it. Second law says if there's temperature difference, heat is going to flow from hot to cold. All right, so within that statement, I want you to notice 2 things. We're talking about the zeroth law, according to which if there's no temperature difference, no heat flow. And the second law deals with what happens when there's a temperature difference. What happens when there's a temperature difference is that the heat is going to flow from hot to cold. Notice that these laws are not in order. All right, I didn't say the first law and the second law. I said the zeroth law and the second law, which means that there's going to be a first law. Obviously, we talked about the second law, and possibly there's going to be a third law. All right, so the zeroth law, you could just kind of gather. It would say who will come up with the zeroth law. All right, you will come up with the first law, the second law, the third law, maybe the fourth law. The zeroth law is an afterthought. All All right, so it's not one single physicist who came up with the laws of thermodynamics. It's multiple people contributing to these laws at various times. And so one day we're reordering the laws. They came up with the first one, the second one, the third one. And then eventually they go, oh, we need to come up with one more law preceding the other ones. And all of a sudden they said, okay, so we got the first three laws are already taken. So let's say we have a zeroth law that comes before the other one. So the zeroth law deals with no temperature difference. If there's no temperature difference, no heat flow. Second law says if there's temperature difference, the heat is going to flow from hot to cold. That's it. All right, so that's your introduction to the laws of thermodynamics. All right, so pick out the best answer and put your answer in there on the side. Okay, very good. Yeah. You guys got it. Okay, Donna, I just saw your question. Okay, we're done with the in-person labs for now. We were doing the in-person labs every other week. So what we'll do is we'll do conceptual labs from now on, and then we will do documentary labs. Okay, so you guys don't need to show up at school anymore. Because we got Thanksgiving next week, so it's not worth for me to travel back to Houston for one day, so it's not going to happen. So we're done with the in-person lab. All right, now that we're talking, all right, guys, let me just extend the 12th. Let me extend the last task, which was available over the weekend. I'm just going to extend it until Tuesday midnight. So 12 of you guys took it. The rest of you guys probably didn't get a chance to. So take care of that. Take care of the upgrade task as well. All right, so we're covering one chapter per week. Just try to keep up with it and try to keep up with the upgrades. If you fall behind, if you miss the task, just do the upgrades for now. All right, I don't want anyone to get less than a C, if possible. All right, so because you guys are taking physics for general education, so let's just not your, it's required for you guys, but there's no reason to fail this course. All right, so these are the best answers, so give yourselves 5 points for that one. All right, so Celsius temperature scale is fairly common outside of the United States. In the United States, we use the Fahrenheit temperature scale. Both temperature scales are based upon the freezing temperature of water as well as the boiling temperature of water. Okay, Celsius scale is a little bit more commonsensical because you take the boiling as well as the freezing temperatures and divide them into 100 smaller pieces. And the Fahrenheit scale is like, you divide it into 180 smaller pieces, but that's the one we use in the United States. All right. In sciences, though, we use the Kelvin temperature scale. All right, so let's talk about the Kelvin temperature scale. All right, let me build you after this one. Let's talk about the tire pressure. All right, where do you get the tire pressure from? Obviously, you get the tire pressure from the air inside the tire, right? And let's assume that the air is composed of molecules. All right, that's an assumption. Just remember, if I were to ask you, what's, you would know that the air is composed of molecules, air molecules. So what happens to the tire pressure when the tires are heated? Tire pressure is going to go up. So the next question is, why does the tire pressure go up when the tires are heated? I'm not putting more into the tire. I'm not putting more air into the tire. If that's the case, why would the tire pressure go up? All right, so a couple of things that we need to unpack here. Number one, we know that the tire pressure is going to come from the air molecules. And number two, more air you put into the tires, the higher the pressure is going to be. So which means that you're increasing the number of molecules that you're putting into the tire, right? And then the tire pressure is going to go up when the tires are heated, but you got the same number of molecules within the tires. So why would the pressure go up when the tires are heated? And then at this point, you're thinking, and you kind of know the answer, right? The answer is because the molecules more than likely moving faster. All right, so when you put heat into the tires, what's happening is the molecules are moving faster, which means that their kinetic energies start to go up. So the reason why the pressure goes up when the tires are heated is because the molecules are moving faster. So if that's the case, what's the relationship between the temperature and the average kinetic energy of the molecules? And all of a sudden you go, oh, as the temperature goes up, all right, so when the tires are heated, temperature goes up, the molecules are moving faster. So the relationship between the kinetic energy, which is the energy of motion of these molecules, and the temperature is a direct one, right? So temperature goes up, the molecules are moving faster, they got larger kinetic energies, and then as a result, the pressure is higher. All right, so this is known as the kinetic theory of gases, which means that the temperature is going to be the average. It's going to be the measure of the average kinetic energy of the molecules. So which means that whenever you're measuring temperature, in essence, that temperature says something about the motion of the molecules. So higher the temperature is, the faster the molecules are moving. So in a sense, you're able to gauge how fast these molecules are moving on average. So higher the temperature is, the faster the molecules are moving. faster the molecules are moving, higher the temperature is. All right, so the argument goes either way. All right, so pick out the best answer. Okay, very good. This is the best answer. All right, I just saw a comment here. Somebody said something interesting, which I like. All right, so Colin says the air expands. All right, Colin, that's absolutely correct. When you heat it up, the air is going to expand, but inside the tires, obviously, the tires will not be able to expand beyond their volume. As a result, the pressure goes up, right? And because the molecules are moving faster and faster. All right, so Colin, give yourself 5 points for that.
Now, there's one more thing I would like to try at this temperature, and that's a football. You know, people do play football games in these incredibly cold climates, like Green Bay, Wisconsin, where the temperature can be 40 degrees below zero. And I often worry about that. I don't worry so much about the football players. After all, they get paid plenty for doing that. And I don't worry about the fans, because anybody who would go to a game on a day like that deserves exactly what he gets. And I don't even worry about the sportscasters, because they're probably inside of a warm broadcast booth behind a plate of glass where they're perfectly safe. What I really worry about is the football itself. Because it does seem to me that being that cold can have an absolutely shattering impact on a football.
Okay, now, unlike the frozen flowers, football does not have any water in it, right? All right, so you cannot make the argument that the water within the cellular structure is frozen, because there's no such thing. There's no water in the football. Yet the football became frozen and just as brittle as flowers. Why? And all of a sudden, if you think about it, what's happening is the temperature dropped quite a bit. So the temperature is related to the average kinetic energy of the molecules, which means that the molecules slow down. And so the molecular attachments became much more rigid, and it became extremely fragile. It became glass-like. It became glass-like, in essence. So that's what happened. As a result, it was able to shatter the football just exactly the same way it was able to shatter the frozen rose or flowers. All right, so there's an interesting thing here that we will kind of explore a little bit. So the Kelvin temperature scale has the lowest temperature at absolute zero. Absolute zero refers to 0 Kelvin. And it is so named by this guy. His name is Low Kelvin. His actual name is William Thomson, Low Kelvin. And it's taken to be 0 Kelvin. And before we discuss the reason for it, a couple of things that I want you to notice. When things are expressed in terms of the Kelvin scale, is the interior of the hottest star is going to be, this is 1 billion Kelvin. And then I want you to take a look at the center of the sun. This is going to be 15 million Kelvin. And then I want you to take a look at the center of the H-bomb explosion. This is 100 million Kelvin. Notice that the center of the H-bomb is 100 million. The center of the sun is 15 million. All right, so this is the power of modern physics. The stuff that we're capable of doing with modern physics is amazing. We can create temperatures hotter, almost 7 times hotter than the center of the sun. And then you start reducing the temperature all the way down. The interstellar space is going to be 3 Kelvin, so I want you to remember that. And then the lowest temperature attained in a laboratory is not quite 0, but it's very close to 0. So why not 0? Okay, so that becomes the question. Why not 0? Why is it that it's not 0? It's not 0 because evidently it's impossible to reach absolute 0. Okay, so through no process, physical process, one can reach absolute 0, 0 Kelvin. So this is known as the third law of thermodynamics. Simply stated, the absolute 0 cannot be reached. So the question is, why not? All right, so there are a couple of reasons for it that we will have to explore. Number one, what happens when you increase the temperature? All right, think of it in terms of the tire temperature. All right, so let's have something that we can relate to. So temperature goes up, the pressure goes up, right? All right. Okay, Devin, just hold on to that question. All right, so when you increase the temperature, what happens is the pressure is going to go up. Okay, so Devin, going back to your question, if the building does not have any windows, if the building is completely contained, if the heat is contained within the building, just like the air inside the tires, yeah, the pressure is going to go up. All right, but you know that's not the case, right? So what's going to happen is the air is going to become less dense and it's going to escape. All right, so if it's a contained environment like the inside the tire, what happens is when you increase the temperature, the pressure is going to go up because the molecules are moving faster. Okay, now let's go in the opposite direction, right? So you start to reduce the temperature. As you start to reduce the temperature, the molecules start to slow down. And notice that as you start to go down to absolute zero, what's going to happen is the average kinetic energy of the molecules will become zero at 0 Kelvin. And then if you go down below 0 Kelvin, it's going to give you negative pressure. What's the meaning of negative pressure? Right? Positive pressure, which means that the molecules are pushing up against the boundaries, trying to just escape. They're moving so fast that they have a hard time staying on the inside. But the negative pressure, what does it mean? It doesn't mean anything in classical physics. Negative pressure does not mean anything in classical physics. In modern physics, it means anti-gravity, but in classical physics, it doesn't mean anything. All right, so as the material starts to cool down, molecules are moving slower, and the measure of the average kinetic energy of these molecules is your temperature on the temperature scale, and the temperature scale is going to tend towards 0 Kelvin, but it's never going to reach 0 Kelvin. So why not? All right, so we'll discuss that shortly. All right, so thermodynamics is what we are studying. All right, so here's a summary of it. If there's temperature difference, there's going to be a heat flow. All right, Q represents heat, T represents temperature, delta means difference. So if there's a temperature difference, there's going to be heat flow. All right, so this means proportional. This is not a Jesus fish symbol. This means proportional. So temperature, the amount of heat that flows is going to be directly proportional to the temperature difference. All right, so bigger the temperature difference is, the more heat is going to flow. Okay, this is the second law. If there's no temperature difference, no heat flow, this becomes the zeroth law. What else do we have? Absolute zero cannot be reached. This is the third law. And there's this first law. Okay, I'm probably gonna okay, first law. Okay, that's the second law. I'm doing it during the lecture or something. I think I'm distracted. The first law. So when you put heat into your system, what happens? The molecules are going to move faster, so their internal energies will go up. This represents the amount of energy that the molecules have. So with the amount of heat that you put into the system is going to become more energized, which means that the molecules are going to move faster. And by the amount of work that the system does, the energy is going to go down. Like you put heat into the car tires, what's going to happen is molecules are moving faster. All right, so they become more energized. But at the same time, the boundaries of the tire is going to be pushed in the opposite direction. So which means that molecules will do a little bit of work to actually expand the volume of the tires. So by the amount of heat that goes into the system, the internal energy is going to go up. By the amount of work that the system does in expanding, the internal energy of the molecules will go down. That's what it means. We will focus on this later. The only thing that we've dealt with so far is the zeroth law, the third law, the second law. The first law is the one that we will deal with later. So don't worry about that one. This is known as the conservation of energy. That's how the conservation of energy was invented. All right, so third law is the one that we're focusing on right now. So absolute zero cannot be reached. Absolute zero refers to 0 Kelvin. All right, so on the Kelvin scale, the higher the temperature is, the faster the molecules are moving, the bigger their kinetic energies are, and the larger the pressure is. So notice that the tire pressure is going to depend on the kinetic energy of the molecules. Kinetic energy of the molecules will depend on the speed of the molecules, and the speed depends on the temperature. Temperature goes up, the speed goes up, the kinetic energy goes up, the larger the pressure is. All right, so that's one way of looking at it. So this is the average temperature is related to average kinetic energy. All right, so there's a formula for it that we're not going to be interested in. The only thing you need to know is the average kinetic energy depends on the Kelvin temperature. Okay, so when the temperature goes down, the molecules are not moving as fast. The kinetic energy goes down. The pressure goes down. When the temperature goes up, the molecules are moving faster. Kinetic energy is larger. The pressure is larger, right? So at absolute zero, so what's happening is temperature is at zero. Molecules are not moving. Average kinetic energy is going to be zero. So there's not going to be any pressure. So the question is, why can't we reach absolute zero? All right, there's a couple of reasons for it. The absolute zero cannot be reached because one argument is if there's temperature difference, there's always going to be heat flow, which is correct. Absolute zero, 0 Kelvin, space, 3 Kelvin, there's temperature difference. So which means that the heat is always going to flow from hot to cold. All right, so unless you can just isolate or insulate a region of space to an extent that there's absolutely no heat flow from outside, there's no way you can reach absolute zero. That's a commonsensical way of looking at it. There's a second explanation you can come up with, which is at absolute zero, the average kinetic energy of the molecules will be zero, which means that some of the molecules will have kinetic energies more than zero. And some of the molecules will have kinetic energies less than zero. Having less than zero kinetic energy makes no sense. All right, you cannot have less than zero kinetic energy. All right, you cannot have less than zero kinetic energy. There are no negative kinetic energies. There's no such thing. What does it mean? Kinetic energy is related to square of the speed of the mass divided by 2. When you're squaring the speed, what does it mean? When you square a number, the negative numbers become positive. You cannot have a negative number. And there's no such thing as negative mass in classical physics. Negative mass means that you got these masses which repel each other. There's no negative gravity. There's no repulsive gravity in classical physics. So it doesn't make sense. You cannot have a zero average kinetic energy. You cannot have them. So that's the meaning of that statement. So absolute zero cannot be reached because there's always going to be a temperature difference. And there's always going to be a heat flow because of the temperature difference. That's the second law. Also, it cannot be reached because you can never have an average zero kinetic energy. There's no such thing. It's not going to happen, which means that some of the particles need to have less than zero average kinetic energies. That's not going to happen. All right, pick out the best answer. Okay, very good. C is the best answer. Give yourself 5. All right, now let's talk about heat. Okay, so it's a restatement of what I stated before. So heat is just a form of energy, right? It's just gonna flow from hot to cold. That's it. This is hot. Your hand is not. So it's gonna go from the pot into your hand. And obviously, ice is cold. Your hand is warmer. So heat is gonna go from hot to cold. It's a form of energy that flows from hot to cold. That's it. All right, so what causes heat is the temperature difference. If there's temperature difference, there's heat. That's the second law. No temperature difference, no heat. That's the zero law. So heat is a form of energy that flows from hot to cold. That's all you need to know.
Miss Martinez, is this your cake spinner with a block of wood you used to slow it down?
Yes, Miss Grimble. That is my cake spinner.
Thank you. Now, Professor Parsons, what would you get if you leaned this block of wood against this spinning disc, like this?
That would be splinters. Oh, no. Okay, now I'm kidding. You would get friction.
Could you be more specific?
No, I could not. No, I'm just kidding again. I'll be specific. You see, friction is a force that tries to stop motion, and friction always causes heat.
Can you show us?
Sure. Jury, rub your hands together like this. Getting warm, isn't it? You feel the heat? Well, that's friction. It's also the friction between the floor and our feet that lets us walk. Now, if the floor was very slippery, the friction would be less and it would be harder to walk. And look at this. Who wants scrambled?
Okay, now watch the thermometer.
Hey, the temperature's going up a little.
What a workout. Yes, that's right. The temperature went up from the friction of water rubbing against water. In fact, I can feel the heat in my shoulder from the friction from moving my arm like that. Ouch.
Michaela, would you please touch the plate and see if it's getting warm?
Sure. Oh, yeah, it's definitely getting warm.
So maybe it gets a little warm. It would never get hot enough to melt the cake or burn the bottom of it.
Mr. Savage, you couldn't be more wrong.
I could be more wrong.
Right. A lot of friction means a lot of heat.
Miss Martinez, how long did you leave the block of wood rubbing against the cake spinner?
All night, Miss Grimble?
All night.
Yeah, but still, to melt a cake like that, you need a lot of heat.
Mr. Savage, have you ever seen a meteor streak across the sky?
You mean a shooting star? Of course, I love those. I always make a wish when I see one.
What do you wish for?
I can't tell you.
Right. Anyway, my point is, a meteor leaves a huge trail of flames as it flies through the sky because friction with the air heats up the meteor and then melts it.
Miss Martinez.
Okay, so let's go back to the definition of heat one more time. So heat is a form of energy that flows from hot to cold. Here we're talking about friction causing heat or heating. How does that happen? I mean, through friction, mechanical energy will get converted into heat, light in the form of fire, obviously. So how do you go from the definition of heat, which is a form of energy that flows from hot to cold, to friction creating heat? How does that happen? All right, so obviously you can generate heat through a conversion process. In this case, the mechanical energy is getting converted into heat through friction. So what's happening is through friction, now look at the surfaces, all right? These surfaces will heat up through friction. So the reason why the surfaces are heating up because the molecules start to jiggle and vibrate through friction. All right, so the faster they're vibrating, higher their kinetic energies are, the hotter they are, right? So the temperature is a measure of the average kinetic energy of the molecules. So the faster the molecules are moving, the hotter the surface is going to become. Larger the temperature is, the bigger the temperature difference is, the more heat is going to flow. So, which means that the heat is being created because the molecules are moving faster. And the surface is going to be at a higher temperature than the room. So the surface temperature is going to be higher than the room temperature. So if there's a temperature difference, there's going to be heat flow. So that's how the energy gets converted into heat. Energy gets converted into heat because the molecules are moving faster. Faster moving molecules is going to be hotter in essence. So the surface temperature goes up, which means that the molecules are moving faster. And the difference in temperature between the surface and the room means that there's going to be heat flow. All right, so this brings us to an interesting documentary.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one, or it's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
All right, so this is probably going to be the strangest thing that we will ever talk about. You guys are taking a physics course which is supposed to aid your understanding of what it is that you guys are going into, and this course originally designed for art students. And this segment is from physics 2, and normally I would teach this in physics 2 at the art school, which is related to time travel and parallel universes. It's more of an investigation. All right, so here's what these guys end up discovering when they were trying to reach absolute zero, the third law. Okay, so according to the third law, the absolute zero cannot be reached. And we have a couple of explanations for it that I gave you, the commonsensical explanations. Number one, there's always going to be a temperature difference. So if there's temperature difference, there's heat flow. So that's going to prevent you from reaching absolute zero. Number two is more of an abstract explanation, which is you can never have an average kinetic energy less than zero. You cannot have negative kinetic energies. So a bunch of physicists in early 1990s, they decided to actually make a really good attempt at reaching absolute zero. They said, okay, so we can isolate and insulate a portion of space to a degree that there's absolutely no heat flow from outside. And then within it, we will just slow these molecules down. All right, so when you slow the molecules down, the temperature goes down. If you can stop them, that's going to be absolute zero. Except all of a sudden, they discovered that when you start to slow these molecules down further and further, these molecules dissolve into waves. So the question is, waves of what? All right, and then all of a sudden, they discovered that the quantum mechanical effects takes place, which means that you end up seeing the same molecule at multiple locations. As a result, the molecule is going to appear at every single location where it could at that moment, every single possible location where it could be. As a result, it gives you this wave appearance. All right, so these waves are seeing the same molecule at multiple locations at the same time. All right, this is known as the many worlds interpretation of quantum theory, usually, which means that notice that this guy is going to start to appear at multiple locations at the same time, which is a version of quantum theory that Hugh Everett III came up with in 1954. And all of a sudden, when these people start to slow things down, and the reality is made up of molecules, that same molecule is going to appear at multiple locations. And you and I are made up of molecules. So which means that it makes sense that you and I are also will appear at multiple locations at the same time, at every single location where you could be at that moment. All right, so that's what these guys are trying to represent visually. All right, so this is, we're not going to put the emphasis on this, obviously. This is more of the modern physics thing. This is something that the art students really, really enjoyed. So this concept comes out of the time travel and parallel universes. Concept comes out of something like this. The third law of thermodynamics usually leads into it. Yours is going to be a little bit more hands-on, so that's the direction that we're headed. I just wanted to point out some interesting facts about this, the third law, why it cannot be reached. Evidently, so the quantum mechanical effects usually takes place. You get to see multiple realities at the same time occurring at the same time. Okay, let's go over the questions. So thermodynamics is the study of heat and its relationship to the mechanical energy of molecules, right? So it's related to how fast the molecules move in their relative positions with respect to each other. Temperature is the measure of how hot or cold something is, but we'll get back to the formal definition. So temperature scales, we got three. We got the Fahrenheit scale that we use in the United States. Outside of the United States, Celsius, in sciences is Kelvin. And the zeroth law of thermodynamics simply states that the two regions at the same temperature. Okay, so if there's no temperature difference, there's no heat flow. Second law says if there's temperature difference, there's heat that's going to flow from hot to cold. So there's going to be heat flow from hot to cold. The purpose of temperature measurement in thermodynamics is check to see if there's any heat, if there's any temperature difference. If there's temperature difference, there's heat flow. If there's no temperature difference, there's no heat flow. Heat is a form of energy that flows from hot to cold. What causes heat is the temperature difference. Kinetic energy is the energy of motion related to speed for a given mass. Tire pressure comes from the motion of the molecules, number of molecules and motion of the molecules. Tire pressure is going to go up when the tires are heated. Tire pressure is going to go up when the tires are heated because the molecules are moving faster. The relationship between the temperature and the average kinetic energy of the molecules is that the higher the temperature is, the faster the molecules are moving. Faster the molecules are moving, higher the temperature is. Absolute zero is 0 Kelvin. At absolute zero, there's no pressure, so the pressure drops to 0. Average kinetic energy of the molecules at absolute zero is going to be 0. So, which means that there would be no average kinetic energy. According to the third law, the absolute zero cannot be reached. Absolute zero cannot be reached, and there's two reasons for it. Number one, if there's temperature difference, there's heat flow, obviously. Space is 3 Kelvin, and so if you're trying to reach 0, because of temperature difference, there's always going to be heat flow. Also, you cannot have average zero kinetic energy. That term itself does not make sense, which implies that you should have negative kinetic energies. You cannot have negative kinetic energies. All right, so that's it for that portion. All right, so